So the physical pendulum, of which the simple pendulum is a special case, is a more general oscillating object. So I've represented it here by a pear-shaped rigid body. So you should think of this as being displaced from the vertical by some angle that is small. I'll soon tell you what small actually means. But right now you think of it as slightly displacing it. Something is hanging from a nail, and you slightly displace it from the vertical hanging position, and then you see what happens when you release it. When you release it, it'll try to come back to its vertical position, but it's moving so fast that it overshoots it and then goes to the other side, and then it repeats this motion back and forth. And we're going to now see that it's a simple harmonic oscillation. So let me indicate the angle it makes the line joining the pivot point P and the center of mass makes with the vertical. I'll call that angle theta. That angle will play an important role in our studies of this motion. So the free body diagram is very simple. There's just the weight acting in the middle, and the distance between the center of mass and the pivot point is called d. So we're going to call this distance d. So if you think about the torque due to gravity about the axis passing through the pivot, that axis is coming out through the paper, that torque is r cross f. So that's this distance cross this force, and so that's going to be out of the page. So that's correctly telling you it's going to swing like that. So the angular acceleration is going to be in this direction. Now observe that theta is measured in that direction, and angular acceleration is opposite the direction of theta. So that will be important in a moment. But the angular acceleration will tell us that the physical pendulum wants to swing like this. So that's the direction of torque, and by Newton's second law, that's the direction of alpha also. So let's write down Newton's second law for this object. The sum of all the torques about the pivot equals the moment of inertia about the pivot times alpha about the pivot. So the torque, I've already told you, is r cross f, but the magnitude of that torque is rf sine theta. So that gives me mgd sine theta. Now observe that theta is in this direction, whereas alpha is in this direction. So to offset that, I'm going to put a negative sign in front of that, and that's going to be equal to ip times alpha. Now believe it or not, we're almost done. All we have to now do is transfer everything over to the other side. So I'll bring I sub p down here, and I'll write alpha as the second derivative of theta with respect to time. So I'll rewrite this in two steps. First, I'll write it as alpha sub p plus mgd over I sub p sine theta equals 0. And in the next step, I'll write alpha sub p as d2 theta over dt squared, because that's exactly what alpha is. It's the rate of change of angular velocity, and the rate of change of angular velocity is again the rate of change of angle with respect to time. So it's a second derivative like that, plus mgd over I sub p sine theta equals 0. Now as written, it is not simple harmonic at this point, because it lacks the cardinal feature of simple harmonicity, which is that this should be theta. It should not be sine theta. But you can readily check for yourself in your calculator that for angles theta, which is about the same or less than 20 degrees, sine theta is approximately equal to theta in radians. Now when you actually try this, when you put your calculator in the radian mode and you verify what sine theta is and what theta is, so in my weekly notes corresponding to this, I've actually put a table out there giving you the value of sine theta, theta, tan theta, and seeing the difference on those things. It'll turn out to be very small. For 20 degrees, I think the answer is different only by 1 or 2%. So it's a very good approximation, and that's why we try to keep our angles of swing in experiments less than 20 degrees in most of the pendulum experiments that you've done so far. So assuming that that's true, assuming this angle is small in this sense, I can replace sine theta with just theta in radians, and I end up getting d2 theta by dt squared plus mgd over I sub p theta equals 0. Well, that looks exactly like the simple harmonic oscillation form that we had in the previous video I showed you, and that was d2x over dt squared plus omega squared simple harmonic times x equals 0, except that the variable x has been replaced by the variable theta. Otherwise, everything is the same. Therefore, we should identify the frequency of oscillation to be that. So let's write the frequency of oscillation for the physical pendulum. Omega simple harmonic is equal to the square root, because omega squared is mgd over I sub p, so omega simple harmonic will be the square root of that, mgd over I sub p. So this is the standard formula for the simple harmonic oscillation angular frequency of any physical pendulum through small angles. Now what I'm going to do next is to tell you how to use this in practice. So let's try a very simple example, and that would be something like a ring pendulum. Let's try the example of a ring pendulum. So I take a ring, it could be any ring like a bangle or a hoop, and I suspend it from a pivot. Let me draw a little picture here. So the equilibrium position, when I let it simply hang for a long time, it'll look like that. But if I displace it from the equilibrium position and I move it like this, then it's going to want to swing back in that direction. So that's going to be your alpha. That's your pivot point. So what are you going to do about something like this? Can we find the period of oscillation? Now, just for reference, the moment of inertia of a ring-like object about the center of mass is, so that's your distance d, by the way, which in this case is the radius of the ring. The moment of inertia about the center of mass of a regular ring is just mr squared. Let's say the mass of the ring is m and the radius is r. So that's going to be the moment of inertia about the center of mass. However, that's not what we want in the formula. We want the moment of inertia about the pivot point. So you have to use a parallel axis theorem. The moment of inertia about the pivot point is equal to ICM plus md squared. That's what the parallel axis theorem tells you, because there is an axis through the center of mass, and that's parallel to the axis that you're using to pivot it. And so that's going to be mr squared plus, where d is equal to r, so that's again another mr squared, so that's 2mr squared. The other thing we need to do is to, well, that's it. There's nothing else to do. So let's just write omega simple harmonic is equal to the square root of m, which is just capital M in this case, g d, which is capital R, divided by 2mr squared. So you find the mass cancels out, which means that all rings, no matter how massive they are, will swing the same way. The radius, one of the radius factors cancels out, and I'm going to get the square root of g over 2r. Now the period is what I want to find. The period of simple harmonic oscillation is related to the angular frequency by the relationship the period equals 2 pi divided by the angular frequency. So if you do that, I get 2 pi square root of 2r over g. So that will be our period of simple harmonic oscillation for this. As another example, let me also tell you how to think about the simple pendulum. The simple pendulum is the simplest object you can think of that could possibly swing back and forth. So it's a point mass. So right now I'll consider just a point mass. Later on I have a video which tells you what happens when you don't have a point mass but you have a bob of some finite radius. What happens then? So you take this point mass, attach it to a string of length L, and since it's a point mass, the length of the pendulum is just the distance between the center of mass of the point mass and the point of pivot, which is simply L. So let's work this formula to find the period of oscillation of a simple pendulum next. This is the second example. That's the first example. That's the second example. So I'm going to get ICM. Well, the pendulum is made up of a point mass, so the moment of inertia is just ml squared, because that's the moment of inertia of a point mass. It's mass times the distance squared from the axis of rotation. And so this is I sub p, not ICM. This is I sub p. ICM is 0 because point mass does not have moment of inertia intrinsically. So that's I sub p. So I just have to substitute it. It has nothing else to do. So omega simple harmonic. You can see how incredibly easy it is to work with this formula. It's just m times g times d, which is same as L here, divided by ml squared. And that's going to be the square root of g over L. I'm playing the same game with the period. T simple harmonic is 2 pi over omega. So that gives me 2 pi root L over g. So that's our classic simple harmonic motion period. Now before, when we did this, I think we did this in lab 2, we were unable to get this factor 2 pi, and this factor 2 pi just comes out by magic because of this definition relating 2 pi over omega and t. Now there's another frequency that I want you to be aware of, and that is called the linear frequency. Omega here is measured in radians per second, whereas linear frequency is measured in units known as hertz. So linear frequency f, simple harmonic, is just 1 over t simple harmonic. It's just a reciprocal of the period. So that's why it's 1 over seconds or hertz. 1 over seconds is the meaning of hertz. So if you write this in terms of omega, because t itself is 2 pi over omega, this is going to be omega over 2 pi. So that's the relationship between the linear frequency and the angular frequency. You take the angular frequency and divide it by 2 pi, and you get the linear frequency. Now, by the way, this is sometimes also used to, this formula for the simple pendulum is so famous that you tend to write every other formula in terms of it. So for example, the ring pendulum is said to be equivalent to a simple pendulum of length 2r. So that's sometimes called the equivalent length of a physical pendulum. So if you have just g in the denominator, if you can arrange for just g to be in the denominator like here, then whatever occurs other than that g, you can bring it to the numerator and it'll be called the equivalent length of that physical pendulum, just to put it in the same footing as a simple pendulum. So if you wanted to replace this ring pendulum with a simple pendulum, all you would have to do is build a simple pendulum of twice the radius. L would be twice the radius, and then if you let this swing and if you let this swing, they'll both swing together.